Hey class, welcome back. This is the last lecture for chapter 7, and today we're going to cover acid-base reactions. Well, and a few other things, but it's mainly we're going to focus on acid-base reactions. Okay, so the first thing first question that you probably have is, what is an acid? All right, and that's a good question. You need to know that in order to understand what's going on in this chapter. So it's important for you to understand, first of all, that there are several types of acids, okay? Several different types of acids, and we will cover most of those in, I think, chapter 13 or 12, but it's in the future. We'll cover those. So for this chapter, we're going to focus on I'm going to introduce to you a specific type of acid. This is called the Arrhenius acid, okay? And the Arrhenius acid, it's important for you to understand that when they are in aqueous solutions, they ionize to form H+, okay? H+ is also, sorry, oops. Okay, H+ is also called a proton. All H+ is a hydrogen atom, right, with one electron, and essentially it loses that electron, right? It gives it up. You can almost think of it like it gives up its electron like lithium would or something like that. And when it gives up its electron, it forms H+, okay? So it's just one proton floating around. So we also call H+ a proton, all right? That's a hydrogen atom without an electron, all right? So Arrhenius acids are substances that once they are put in water, in aqueous solutions, once they're put in water, they ionize to form H+. A good example of this is HCl, hydrochloric acid, right? I put AQ there, it's soluble in water. And what ends up happening is that you can almost look at like this as like as an ionic compound, okay? Where hydrogen almost acts like a metal, and in this case it does, and it ionizes, this guy ionizes to form H+ and Cl-, all right? And it's the fact that this H+ exists makes this guy an acid, all right? So a lot of times you'll see acids, they have a hydrogen, an H, right, at the beginning of their formula. So that is called an Arrhenius acid. Arrhenius acids ionize to form protons or H+ in solution, in aqueous solutions. So the opposite, right, of an acid is a base. All right, so it's important for you to understand what a base is as well. There are, this should say, sorry, I should have fixed this. There are several types of bases, all right, but when we're talking about Arrhenius acids, we're also going to have Arrhenius bases because they exist in pairs, all right? Acids and bases exist in pairs. So it's kind of hard for you to see. Oh, there it is right there. So Arrhenius bases ionize in aqueous solutions to form OH-. This is remember, this is a hydroxide ion. So an example of this would be sodium hydroxide, NaOH, right, aqueous. So when it ionizes in water, it's going to form Na+, which is not very relevant in acid-base chemistry. It's the OH- that's relevant, okay? So this OH-, that's the guy that's important, all right? And again, so when we see acids, we look for this Arrhenius acids, we look for the H, hydrogen, and Arrhenius bases, we look for this hydroxide ion, and we know that if this is soluble in water, it will ionize to form OH-. So acid-base reactions are reactions that form water and a salt upon mixing of an acid and a base. All right, so this is what HCl and NaOH. And I'm just going to, like I said, I'm just going to break these guys up again. So we have H plus Cl minus plus NaOH, right? And this guy is going to, so we're going to look at, I'll just do this in red. So this hydrogen, well, first of all, before we do the hydrogen, let's look at the chloride. The chloride and the sodium cation are going to come together, right? They're going to form NaCl. It's soluble, so it's going to keep it Cl minus. Remember, this is the, actually what I'm doing right now is I am writing the complete ionic equation. And then we have this H plus that interacts with that OH. So the acid is going to interact with the base essentially, right? And it's going to form, if you have H plus and OH minus, that's going to make H2O. All right. Now, and here's where the H2O is up here. All right. So this below is the complete ionic equation. And above here, this is the molecular. All right. This is the molecular equation right here. And again, so what ends up happening is this acid and base mix to form water. So here's our H2O and a salt. A lot of times the salt is soluble, okay? And since the salt is soluble, right, we break it up down here for our a complete ionic equation. Now let's say we wanted to write a net ionic for this. So again, I'm going to do this in pink, the net ionic. So remember what the net ionic is? The net ionic is, we take out all of the spectator ions. So it looks like Cl is a spectator ion, and it looks like sodium is a spectator ion. So for our net ionic, we have H plus, excuse me, because those didn't go together, plus OH minus forms H2O. All right, so you will notice here that this really fast, this forms water, and I don't have aqueous underneath next to this. I have liquid, right, because that's kind of redundant to put aqueous here. So we have liquid water. Because we have liquid water here, when we write the complete ionic, we don't break it up. It does not ionize. Water does not ionize like this. There is such a thing as called autoionization of water. We'll talk about it later. But for these types of reactions, water doesn't ionize. It is now a molecular compound. So when we write our complete ionic, we don't break this guy up. We keep it together like we would keep a solid together in the precipitation reactions. So that means since we don't break this up, this comes down in our net ionic. Okay? So this right here, this net ionic, is always these acid-base reactions, right, for this chapter that form water and a salt. If the salt is aqueous, this is always going to be our net ionic, our net ionic. H plus OH minus goes to water, okay? And it's really important for you to be able to break these guys up, because once you break up the reactants into their respective ions, it shows what's the acid and what's the base, all right? Base is always ionized to form OH, hydroxide ion, and acid's always ionized to form H plus. This is the same thing that I just wrote right here. Acid-base reactions, also called neutralization reactions, right, generally form water and an ionic compound called a salt, all right? The ionic compound here called a salt, that's our NaCl. That's the generic table salt. Usually it's soluble, so it remains dissolved in solution. And again, for many acid-base reactions, the net ionic equation is just like this for what I showed you right up here. Okay, it's H plus OH minus goes to water. So here are some, we skipped naming acids in chapter 7 because with this, because we lost a whole week. and then we had to transition online. There just wasn't enough time for it. So here is a table of some very common acids and bases. And so I'm going to take you through it really fast, and I want you to understand what you're looking at. So we'll focus on acids at this point. So here we have hydrochloric acid. Hydrochloric acid is pretty, if you think about it, if you just look at this, you can kind of think of what it is. You have hydro, so think hydrogen, right? So that's the hydrogen right here, and then chloric, Cl, that's the chlorine right there, and then acid, so you know that the hydrogen is going to come first, okay? The next one, hydrobromic. Hydro for H, and then bromic for Br. Nitric acid's a little bit different, okay? Nitric acid, since you see acid, think H+, all right? But this nitric part, that's your nitrate, right? And instead of saying ATE, it's IC. So you remove the ATE, so it's nitric acid. So that's, and then the big, really important part for this one is H+. So also, I'm going to write next to these what they ionize into. So H+, Cl-. This is H+, Br-. This is going to be ionized into H+, and NO3-. Sulfuric acid, all right, right here. Sulfuric acid, sulfuric, you can think of that as sulfate, right? And then we have 2 protons right there, or 2 hydrogens, right? So H2SO4 is going to ionize essentially into 2H+, and then SO4, and you guys remember what the charge is on sulfate, it's 2-. Right, those 2 protons are there to balance out the charge. Again, we can think about, for acids, we can think about protons as being, almost like a metal, right? Perchloric acid is another one. So let's go ahead and do perchloric acid. Right, big take-home message right here, H+, so it's going to ionize again into H+, and ClO4-. And then another common one is acetic acid, right here, and that's going to hot ionize into H+ and acetate, which is a polyatomic anion, all right? So again, take home message with all these acids, all of them, and I'll do this all in a different color so you can see what I'm talking about. The big take home message for these is that you see they all have H right there. That is, once you see that H up front, think acid pretty much, okay? Now we're going to go over to these bases, all right? These are all really pretty obvious because guess what? They all have OH associated with them. All right, so when you throw these guys in water, first of all, it's an OH. It's always an OH with a metal. All right, these guys are H pluses with an anion. All right, some kind of anion. These are going to be OH is the anion, and then it's associated with some type of metal cation. So we have sodium hydroxide, sodium Na, hydroxide, OH. So this guy is going to dissociate, be crazy and do green, Na plus, OH minus, all right? Again, hydroxide, anion is always a -1. Lithium hydroxide dissociates into Li plus, OH minus. Potassium hydroxide, K plus, OH minus. Calcium hydroxide is going to be Ca2 plus. Let's zoom in. Okay, so that's going to be Ca2, goodness, 2 plus and 2OH minus. And this is barium hydroxide, all right? So barium dissociates once you throw it in water. Ba2 plus and 2 hydroxide anions. And if you're wondering here why I did here, this is actually more correct. We like to write the superscript negative symbol on the oxygen because it's really the oxygen that carries that negative charge, not the hydrogen. That's because oxygen doesn't share that electron density equally. So there's going to be more electron density on on oxygen. Okay, so these are some common acids and bases. Again, for the acids, you look for the H plus or hydrogen, and for the bases, you're going to look for this OH. And this is how they all dissociate. So you can mix and match all of these and write all different kinds, all sorts of acid-base reactions. All right. So let's do one right now. So this is nitric acid, right? HNO3, nitric because it's nitrate, but since it's the nitrate anion, but since we have an H here, we replace the ATE with IC, so nitric acid. So this is our acid plus calcium hydroxide. And I'll just go ahead and break this guy up. If we have to predict the products, what I like to do is I like to write it out underneath, so it's going to be H plus NO3 minus. We can do this. This is aqueous. I did not. This is kind of a typo. I did not write the phases right here, but calcium hydroxide is also soluble. Okay, so plus Ca2 plus 2OH minus. All right. Now we're going to take, this is kind of the same thing. We're going to take the cation from the first compound and pair it up with the anion from the second. Now here I only have one hydrogen. Here I have 2 hydroxides, so I'm going to have to put a 2 here. So if I put a 2 there, I'm going to have to put a 2 up here, and I'm going to have to put a 2 down here. All right. So now this is balanced, so I can go ahead and write, this is going to make 2 moles of water, and I'll do subscript L. That's my lowercase l. It's always I always do it in parentheses. Now the cation from the second can pair up with the anion with the first compound. And look, since I threw that 2 right here, this and this is already balanced because this is a 2 plus. This carries a 2 plus charge. Each nitrate carries a -1. Now that I have 2, I can pair these up just fine, and it's going to give me calcium NO3 2. All right. And is this soluble? It should be because all nitrates are soluble. All right. So if I wanted, so just to let you know, just to make sure, did it form the products that we wanted? We're looking for a water, and look, there's your water, and a salt, and there's your salt right there. And just to, complete the whole thing, let's do the total ionic. So the total ionic, because this is water, we have to bring this down. This is a molecular compound, right? It's not ionic. And then our calcium, since it's aqueous 2 plus, we're going to break it up. All right. Now let's do I'll do the net in pink. So to do the net in pink, we're going to remove all of our spectator ions, and that means that this is gone, and this is gone, and this is gone, and this is gone. So that's going to give us 2H plus 2OH minus goes to 2H2O. So this is the net. All right, so that follows exactly what we were looking at before. The net H plus OH minus goes to H2O. All right. Let's do one more. We have sulfuric acid, and we have potassium hydroxide. So sulfuric acid, it's going to dissociate into 2H plus and SO4 2 minus plus K plus OH. All right. So we have, again, we have 2 hydrogens here, and then we only have 1 hydroxide anion on right here. So I'm going to have to put, here, this is a little messy anyway. I'm going to have to put it, I'm going to do this too. All right, so since we have 2 here, we're going to have to put a 2 there and a 2 here, right? I have to put a 2 there. So now we're good. So I can start completing. So 2H plus, 2OH minus, that gives me 2H2O liquid plus K2 SO4, right? And that should be aqueous. That should be aqueous. It's funny, I'm going to just, right now, I am looking at my, give me just a second, I'm looking at my solubility chart just to make sure. Oh, here we go. Yeah, so sulfates are mostly soluble. They're just not soluble with lead, calcium, strontium, or barium. All right, so that is that potassium sulfate is aqueous. So now when I write my total ionic, I'm going to bring 2H2O down because now it's a molecular compound and I can't break that up. Right, you can only break up ionic compounds that are soluble, like this one. And we have 2K plus SO4 2 minus. Now, just to make things, I'm going to complete, I'm going to do my net, and I'm going to remove all the spectator ions. Which gives us, again, 2H plus plus 2OH minus goes to 2H2O, right? And that's my net. Okay? So, these are acid-base reactions, all right, that form water and a soluble salt. So those are pretty straightforward. Again, like I said, it's just important for you to understand what is an acid and what is a base, and I color-coded the acids and bases for you so you could see, but I also went through all of this, so you shouldn't have any problem understanding how they break up or how they ionize into in solution, in aqueous solutions, and then doing the net ionic, and then the total ionic is the same type of process that it was for the precipitation reactions, okay? You bring down, for the net, for the total ionic, you're only going to break up the compounds that are aqueous and that are soluble. Water is a molecular compound, so it's not going to ionize in the way that calcium nitrate will. All right, so you're going to bring that all the way through. All right, so this brings us to gas-evolving reactions. Okay, so gas-evolving reactions occur when we react something with something else, and the product that initially is formed is unstable. All right, so how would you know that it's unstable? Well, you would know it because I'm telling it to you. All right, so these are the products that are unstable. All right, these guys right here, NH4OH, H2SO3, and H2CO3. All right, Those essentially are so when you see those in your products, you got to think ding, 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 gas evolution reaction. All right. What happens is once you form these products, and so we call them intermediates because they quickly decompose. They don't stay they quickly decompose into gases. All right. So the reaction might not want to form a reaction or form a gas on purpose, or that wasn't the goal. It's just the product that was formed, these guys right here, are unstable, so they quickly decompose into gases. All right, so this bicarbonate right here, H2CO3, I'm sorry, no, that's just carbonate. Anyway, it is going to evolve, it is going to decompose into CO2. Sulfates, this guy right here, H2SO3, that is going to decompose into SO2, and this guy right here is going to decompose into NH3. Let me give you an example, okay? Take-home message for this slide, though, is that remember, if you make this in your product, they're going to decompose into something else, okay? Here are some examples. All right, and I'll do the first one. I'll do this one down here so you can see it. All right, so let's say you have a word problem that says hydrochloric acid reacts with potassium sulfide, right? Or let's just say you have that, all right, and you don't know what else to do. You're just like, write everything out, all right? Hydrochloric acid reacts with potassium sulfide to form something. So write it out. And so first of all, you're going to write HCl, and you're going to say plus K2S, all right? They're also both aqueous. All right. So the first thing I do is I go right below it, and I start the total ionic first. This is the molecular. Right? So I'm going to break this guy up, H plus. So this is an acid, Cl minus, plus 2K plus. Where did I get the 2? I got the 2 from here. Goes 2. All right. Now I can sit there and I can pair everybody up. The cation from the first compound is going to react with the anion from the second, right? So this H plus is a +1. This sulfide is a 2 minus. So I need to put a 2 here. So if I put a 2 here, I have to put a 2 here. And since I put a 2 here, I have to put a 2 here. So I'm going to erase this really fast. And I'm going to put a 2. And then I'm going to change it back to there we go. All right. Now these guys can pair up. So 2H plus, S2 minus, we're going to have H2S. And then we're going to have, we have our our metal, or our cation from our second reactant, is going to pair up with the anion from the first, and that's going to form, it's a 1-to-1. So that's going to form, let's see, I don't know what this is, plus 2 KCl. All right. KCl is soluble, so I'm going to put an AQ here. All right. And the big question is, what is this H2S? This is hydrogen sulfide. So this is actually a direct gas forming product, right? Because there was no intermediate product. It just formed this. And so you have to, you'll probably be given a table like this anyway. So what you would have to do is, if you were like, oh my gosh, I don't know what H2S is, you'd have to consult this table and recognize that it is a gas. So since it's a gas, put a G here. Now to finish my total ionic, I have to bring the gas down, right? Because it's not a, and it's not a soluble ionic compound, so I don't break it up. right? And then I always do my net in pink. I don't know. That's just a thing I started off. So we're going to do net. Remember, we're going to remove all the spectator ions. So KCl, or Cl gone, Cl and potassium. So my net is going to be 2H plus S2 minus goes to hydrogen sulfide gas. All right, so that's the first one. That's this one right here. All right, and we will do one more. Let me see if I can duplicate this. Add page. See if I can do that. Oh, it didn't work. Okay, so we'll do sorry, just bear with me. Oh, that's not what I wanted to do. I'll go back to here. Okay. So you have this down. Let me just go ahead and do the next one. And I'll just have to, well, actually, let's do this one. Nitric acid, and I gave you what it was because we didn't go through amine acids, reacts with sodium carbonate to form what? So we'll say HNO3 reacts with sodium carbonate, so Na, right? Sodium is always an Na plus, whoopsies, and carbonate is a CO3 2 minus, all right? So we are going to need 2 sodiums for every 1 carbonate. And according to my solubility table, it should be soluble. Yes, and carbonates are usually not soluble, but when they're paired with lithium, sodium, or potassium, so a smaller cation, they're usually soluble. So I'm going to put AQ here. All right. So now I'm going to break this guy up because this guy is soluble. So H plus NO3 minus plus, oops, I don't know what that means, plus 2 Na plus CO3 2 minus. All right, now we're going to pair the cation from the first to the anion the second. You'll notice that the H plus and these guys don't cancel out, or so we're going to have to put a 2 here. So if I put a 2 there, I'm going to have to put a 2 here, and then I'm also going to have to put a 2 there. All right. So now that I did that, I will form, looks like those cancel out just fine, those balance out just fine, so I'm going to go ahead and say H2, right, CO3 plus, and then the cation from the second is going to pair up with the anion from the first, and those balance out nicely. So we're going to have 2ANO3. All right, so then you look at this and you're like, I have no idea what this is. I don't know what's going on. It looks weird. And then what you want to do is you say, well, is this a gas evolving reaction? I'm not sure. H2CO3, is that a thing? So let's go back up and look at that. H2CO3, this is an intermediate. It quickly decomposes into CO2. But it can't just be CO2, right? There's no way. It can't just be, because this is just CO2. Where does the H go? Where do the hydrogens go, and where does the extra oxygen go? So let's go back down here, and let me just show you. H2, CO3 will decompose into CO2, which is a gas. All right, so we got this, right? And we have one oxygen, or two oxygens that we used, right? So if we have two oxygens that we use, then we would, two oxygens, so that leaves us with one O. So is there a compound that is made up of two hydrogens and one oxygen? Yes. So this guy is going to decompose into CO2 and water, balanced. So what you want to do is I'm going to just delete that really fast. What you want to do is you could mark this out right here, and you're going to say 8. The CO2 gas. All right. Now we can complete the net ionic by bringing down H2O liquid. Again, we're going to bring that down because it's a covalent compound. CO2 is also a covalent compound. It's a gas, so it's not soluble in, well, it is slightly soluble in water, but that's not what we're getting at right now. And then we're still not going to break it up because it doesn't ionize. 2Na plus, comma, 2NO3 minus. All right, now we're going to do our net. So we're going to take out everything that we see. So nitrates are gone, sodium is gone, and yep, so it looks like our net is going to be 2H plus CO2 3 minus goes to H2O liquid plus CO2 gas. And there you go. So you can see that even though we made this guy right here, all right, because from our chart, right, this is going to quickly decompose into CO2. That's the gas that's evolved, right? Because this says gas evolved, they're not going to put water here, but water does go there. Or it does also make water, okay? Same thing with this, right? You can see here that NH4OH will decompose. It's going to take to NH3, so that's going to be, this is gone, and then 3 hydrogens are gone, so that's going to leave H2O. Same thing with this guy right here, hydrogen sulfite, right, is going to decompose into sulfur dioxide gas and H2O, right? So H2, sulfur here went here, and then the O2, 2 of the oxygens went here. That leaves that 1 oxygen. So it's all, it's going to be these gases and water, all right? So, okay, we'll keep going. So this is just right here. This is the exact same thing that I did up here and here, all right? Yes. We have HNO3 plus sodium carbonate, right? The only thing that they did differently is they didn't balance until the end. They did not balance until the end. I like to balance after, or while I'm doing it. While I'm doing it's always nice for me to write out the skeleton equation, the reaction part of the skeleton equation first, then jump down to the reaction portion of the total ionic and then that is where you balance, right? And then if you balance this, you're going to balance this, and then anything that you put over here will automatically be balanced. So I like to do it that way. But like I said, the book does it a little bit different. I posted this so you can see everything. So let's take you through everything that we've learned so far. All right, we've talked about chemical reactions. We've talked about what is evidence of a chemical reaction, all right? Gas formation, light, absorption of heat, or heat emission. We talked about color change, and we talked about solid formation, all right? So solid formation are these precipitation reactions. Acid-base reactions can also be gas-evolving reactions as well, all right? And an example of that would be, that's technically one, but we go back up here. You know, this is technically an acid-base reaction, all right? But don't get too confused about that. So acid-base reactions, gas-evolving reactions, talked about that. We did not talk about oxidation reactions. We're going to skip that, all right? Oxidation reactions are, you'll learn this in 200. If we had time, I would like to teach it to you here because they're fun, but they're also kind of confusing and hard. So we're just not going to worry about it. It's going to be hard to teach online. And then we talked about combustion reactions, but a quick refresher of combustion reactions. Combustion reactions are always a hydrocarbon. Right? Hydrocarbon will be something like methane, CH4, plus oxygen, right? And then some kind of heat source, small heat source, and then that'll give you CO2 and H2O. Okay, so it's a very, we don't spend a lot of time on it because they're very important reactions, but they're not very difficult to identify. If you see something, if you see a hydrocarbon, any type of hydrocarbon, anything that has carbon and hydrogen, that's it, react with oxygen to form CO2 and water, that is always going to be a combustion. All right? So we've learned precipitation reactions. Now we know acid-base. Now we know gas evolution reactions and combustion reactions. Okay? So there's another way of classifying chemical reactions, and we do that by what atoms do, all right? And you probably have heard double displacement reaction by now. Double displacement. Every single precipitation reaction that you have done in lecture and that you have done in lab is an example of a double displacement reaction, all right? So this is just another way of classifying these kinds of reactions, all right? So I'll take you through them really fast. There's synthesis or combination reactions, and that's very straightforward. You take one thing and you add it to another thing and you make one thing. So you're synthesizing, you're making something. You're combining two things into one. The opposite is a decomposition reaction. You start off with one thing and it decomposes into two things. You have a single displacement reaction where you have A by itself and then you have B and C, and then what you do after the reaction, A and C are now together, right, and B is by itself. So basically, A just reacted with C, and B was left by itself, all right? And then the other thing is, again, double displacement. This is where everybody swaps partners. A and B were originally together. A is going to react with, let's say, D, and B is going to combine with C. All right, so you have this, and you have that. All right, so I'll take you through some examples. So again, synthesis reaction. Two simpler substances combine to make one more complex substance, all right? A really good example of this is, sorry, this is so small. All right, you have solid sodium and you have chlorine gas, and we balance, this is one of the first reactions that we even balanced, is it makes 2 moles of, so 2 moles of sodium, solid, react with 1 mole of chlorine gas to give you 2 moles of NaCl, all right, solid. This is a perfect example of a synthesis reaction where A, and then you have B, and then you have A, B, okay? Very straightforward. Decomposition reactions, very similar. And in this example, we have water undergoes electrolysis, all right? So you have water, H2O liquid, undergoes a decomposition to form O2 and hydrogen gas, all right? So this is not balanced right now, so don't worry about it, but long story short, we have a complex substance decomposes to form simpler substances, all right? An example, electrolysis, right, is electrical current that is passed through water. The water undergoes a decomposition to reaction to form hydrogen gas and oxygen gas, okay? If you really wanted to balance this, if you're like, how would you balance this? This would be completely acceptable. I never liked those though, but that's how you would do it. I like those that have fractions as coefficients. I don't know, makes my skin crawl, but it's correct. Oh, I guess they did it down here too. That's another way to do it. All right, so you could do 2H, 2O, 2H2, and then just a single oxygen. That's fine. Single displacement reactions, all right? This is where one element displaces another in a compound. We would have done this in lab if we weren't under lockdown, all right? But again, a simple reaction would be where you take solid zinc and you dunk it in a copper chloride solution, and it turns out that zinc is more reactive than copper. So what happens is zinc switches places with copper, and then you end up making zinc chloride and solid copper. All right, so actually I'll write this out. So we would have zinc, solid zinc, plus CaOCl2 aqueous goes to, zoom in again, zinc chloride aqueous plus copper solid. All right, so swapping partners, or, we can say A in the form of zinc displacing B, which is copper, all right? So so oftentimes the reactance is an element A just by itself, an ionic compound, or an acid B. This is an ionic compound, it's not an acid, to form an ionic compound again and an element. So I'm just going to go through this with you really fast. We have an activity series to determine whether or not something will react. So I wrote on the previous slide, right, that zinc is going to displace copper. It's going to kick copper off, make copper form a solid, and it's going to now form zinc chloride. The only way we know that this will happen is we have this thing called an activity series, and it's very easy to use. You just basically have to locate both metals in the series, and if one metal, zinc, so the metal that's by itself, if it is stronger or more reactive it will displace copper. Okay, so how do we know that it's more reactive? We have an axis, right? And this is increasing activity right here. This is increasing activity. So zinc is right here. I'll have it. There's zinc. That's zinc, right? So the only way that zinc won't replace copper is if it's higher in the activity series. And look at copper, it's way down low. So zinc is much more reactive. So since zinc is reactive, you can easily just go ahead and say, all right, they'll swap out. Zinc will replace copper, AQ, and copper will deposit as a solid. And the whole reason this is because we're looking at metals right now, and metals, if you want to think about reactivity, what do metals do? Metals give up electrons. That's what they do. So if a metal is more reactive than another, and what we can start back and we can look at this scenario right here. In this scenario right here, zinc hasn't given up any of its electrons, right? Because it's only zinc. That's it. Copper has given up its electrons to chlorine, to form chloride, right? So if we were to break this guy up, it would be Cu2 plus 2Cl minus. Those two extra electrons on chloride are there because copper gave it to chloride. So, but when when zinc comes into the situation, since zinc is more reactive, it wants to give up its electrons more than copper. So what ends up happening is zinc ends up pairing with chloride here, and copper is forced to, we call it plate out, but form a solid, right? So whether or not copper takes its electrons back from chloride and then zinc gives it to it, we don't really know. Either way, we know the end result. The end result is, because zinc is more, and I'll do this in red, because zinc is more reactive, the end result is that zinc is now a 2+, right? And copper has no charge on it. It's a 0 because it took back electrons, right? Because copper was a 2+. It was a 2+ at the beginning. But since a more reactive metal came up, right, that more reactive metal displaced copper. Okay, so that's how we use the reactivity series. Sorry about that. There you go. If I'm moving these slides too fast, let me know. Just somebody send me an email and be like, hey, you're just all over the place. I'll be like, all right, I'll try to slow down. So let's look at another one. Oh, I already went over this. So again, if A is more reactive than B, right? So in a displacement or single displacement reaction, element A displaces element B only if A is more reactive. So here, A is zinc, B is copper. If A is more reactive than B, they'll swap places. So let's look at these two right here. We have solid magnesium and we have nickel nitrate. All right. So first thing we have to do is we have to locate where solid magnesium is on the activity series, and it's right there. And where is nickel? Oh, nickel's all the way down here. So looks like if I just want to finish this, all I need to do is just say, all right, they're going to swap places. So it's going to be Mg and oops. Mg, they're just going to swap plus solid nickel, right? Another reaction, mercury is placed in a solution of copper 2 sulfate. So here, mercury, now I have liquid because mercury is always a liquid, and then copper 2 sulfate, so that's this right here. Now, first thing you want to do is locate where mercury is on the reactivity series? Mercury is down here. Right? And where's copper? Copper's above it. So since copper's above it, we're going to have no reaction. All right? Mercury is not strong enough to replace copper, so nothing's going to change. Do one more. Now this is a little bit of a different one, but it's still, because we're looking at halogens. All right? I also want you to notice that hydrogen on the metal side, hydrogen's right there. Okay? So if you have an acid, right, you're going to look at hydrogen as if it's a metal and use the reactivity series in the same way. Okay, so let's say we have halogens right here. So we are, in this situation, we are comparing essentially two halogens. Bromine is placed in a solution of potassium iodide. This is actually directly from one of the labs that you did miss, but it's still important to understand how to use the reactivity series for this. So here we have bromine and we have iodide. I put the B over potassium, but really it should be over iodide, right? And what we're looking at is which one's stronger, which halogen is stronger. Is it bromine or is it iodide? Remember what nonmetals do. Nonmetals give up electrons. So the more reactive, that's not metal. The more reactive nonmetal nonmetals take electrons. The more reactive metal wants electrons, all right? So here, right, the charge on bromine, it's a covalent compound here, it's 0. Here, the charge on iodide is -1. So, if bromine is more reactive than iodide, they will swap places. And we look on the reactivity series. Bromine is here. There's bromine, and here's iodide. Bromine is higher up. So since bromine is higher up, yes, they will swap places, and we will end up having, I'm not going to balance this just to let you know, okay, just for time purposes. So we end up having K. Why is my thing not ready? Right, they swap out, so I guess I can do, if I did a 2 here, fine, I'll balance it. All right, 2 kBr. So let's look at what's going on. Remember I said nonmetals take electrons, and the more reactive nonmetal wants electrons. So since bromine is more reactive, bromine started off with 0 charge on it, right? We can also call that an oxidation state, but it's a charge of 0. Now it is what? Br -1. I2, or iodine, was -1. Now it has, because it's in its diatomic form, it's in its covalent form, its charge is now 0. So that is why they switch. That is what it means to be more reactive in terms of halogens. Okay, so that is how we use the reactivity series for single displacement reactions. Double displacement reactions, I'm going to just briefly go over, but these are all precipitation reactions. It's where, remember, the cation from the first compound reacts with the anion from the second, and everybody switches, all right? This is precipitation reactions, these are acid-base reactions, and these are gas-evolving reactions. So anytime you hear double displacement, that's all these types of reactions, and it's just where everybody swaps partners. And then finally, we have combustion reactions right here. Again, all I asked you to understand is that you're looking at a hydrocarbon. So this subscript X and subscript Y could be any integer. right? And so some type of hydrocarbon. Hydrocarbon could even be O, CHO, all right? Either way, hydrocarbon plus oxygen goes to, big take-home message, CO2 and water. You just need to be able to identify what combination reactions are. I'm sorry, combustion reactions are. In general, combustion reactions consist of hydrocarbons reacting with O2 to form CO2 and water. And that's all you need to know. Here's a quick summary of everything that you learned at the end, okay, and how some of these reactions that we learned at the beginning, precipitation reactions, acid-base, gas-evolvent reactions, those are all a part of double displacement, all right? We talked about single displacement and being able to use the reactivity series. You can easily identify combination and synthesis reactions. We can also balance these if we need to, and then we also know how to identify combination reactions. Okay, I'm going to stop here. That is it for Chapter 7. We will pick up. So this is essentially the end of what would be this Tuesday's lecture. Okay, and I will upload some more lectures soon. Thanks for listening.